Hello there. Let's talk about representing an unweighted, undirected graph in your machine using an edge list representation. Okay, so hopefully you watched my previous videos. If you haven't, you might want to take a step back and check them out. We talked about, what is a graph? What are some basic rules and terminology of a graph? Not graphing paper, but a graph. And we talked about representing paths in graphs using either a list of nodes or a list of edges. And we're going to take the edge list concept one step further, and we're going to actually just say this whole graph is being represented as an edge list. It'll make sense in a little bit. But so the first thing I'm going to do is try to set up my stuff, which is always set up wrong because I'm the one setting it up and it always gets messed up. Okay, so I got a graph paper, and I got to make this other thing full screen. Sorry. I'm going to draw a random graph just real fast. So I'm going to do, I don't know, just some random nodes. So remember, a graph is a collection of nodes and edges. Doesn't even have to have edges, but we'll just say. So we're going to do, that's bad. Let me try one more time. We'll get that. Okay, so I'm trying to get this circle perfect because I'm going to have to duplicate it. Okay. So I've got a node here, and I'm just going to give it an arbitrary value. I'm going to say it's got a 3. And then I'm going to duplicate it a few times just to make a graph that is a little bit interesting. So we have something to kind of challenge us, I guess, so it's not incredibly boring. And then I'm going to change some of the values here, and then, well, I'll change the next ones. And then we'll start looking at edges. Which edges do we want to make? Okay, so right now we're just making a graph. Make this graph along with me if you want to, or, after you think you understand, do another graph on your own. Okay, so I'm going to make some edges right now. Remember, this is going to be an undirected, unweighted graph, so the edges are just going to be lines. They're not going to have direction on them, and they're not going to have weights on them. I'm going to do a line over here. I'm just randomly doing lines. Doesn't really matter what we do exactly. The point is going to be, let's practice representing this graph. Okay, so I'm just making a random graph. It's kind of like a little bit dense. I don't know. Maybe I'll just stop there, and then I'll add a wonky line just to prove we can be cool about this. I don't know. We'll do another one right here. So it's a slightly more interesting graph. Okay, so that's just a graph, and what I'm going to do is I'm going to say this is a an unweighted, weighted, undirected graph, and we're going to use the edge list representation. I have spell check on this? I really hope I do. Nope. Okay. I guess I forgot to fix that months ago. All right, so then the next thing we're going to do is we're going to look at the idea of, like, how do we start with the edge list representation? Okay, the first thing I'm going to say is that our graph in an edge list representation is a tuple, just meaning it's, some things put together, if you know tuples in coding already. The tuple is going to consist of a collection of vertices and edges. Well, it's going to be an edge list. Don't make fun of my E's, please. Anyway, so let's do the first thing is going to be the vertex list. So how do we represent the vertex list or the node list? Well, I'm just going to say that my vertex list V is equal to something. And we'll just put inside of this some vertices. So the easiest way when you're kind of drawing this right now is I'm just going to start putting the values of the nodes. I'm going to say, well, here's a 3. And I guess I could sort them for whatever reason if we want to do binary search on them later, but we're not going to. I'm just going to, maybe, I'll go from left to right. So that'll make more sense just visually. So I'll go from left to right. 3, 13, 6, 12, and a 15, and an 18. You can see all of those are nodes, right? Somebody stop me if I forgot a node. Okay. Here's the thing, though. What are we actually storing in this vertex list? You probably don't want to store the node values. I mean, you could. Be a little slow and dumb, though. But we want the option to be a little bit faster later, and also the option to, turn these vertices into full classes, like give them extra properties and whatever. So what I'm going to say is that I'm writing down the number 3 and the number 13 here for you, but you should imagine in your code, you would have an object of type vertex or node, like a full class, and you would basically be stuffing pointers inside of that vector, inside of that list. I keep saying list It is called an edgeless representation, but you can probably imagine that this could just as easily be a vector. If you've seen my other videos, you know what that is. But so I want to be able to index this faster. So for me personally, I make this a vector and not an actual list, but we're going to call it a list. Anyway, so 3 should be a pointer to a full node object. Smart pointer, raw pointer, whatever you want. 13 should be a full pointer to an entirely different node object with just 13 assigned as its template type value. Because we're making this a vector, we can actually index the nodes, right? So like this is like index 0 for the 3 node, index 1 for the 13 node. So I'm just going to put the indexes here. Whoops, just to drive the point home a little bit further. So if I told you, hey, let's do the node at index 2, you would know that is the node that is in the very middle with the value of 6, because index 0 and 1 and 2 brings you to this node right here, which is a 6. So this is gonna help us later. Let me save this real fast, by the way. Just gonna do that. Okay. So the next thing that we need to do is make an edge list. The edge list is really where it's all at. That's really where all the data is. It's going to tell us exactly where everything is, or it's going to describe the whole graph pretty much. So the edge list is another, we'll say that's a list. This could be like a linked list or vector or whatever you want. I'm just going to say it's a linked list. And every item in the list is going to be another tuple. So remember above the graph itself was a tuple containing a vertex list and an edge list. So the edge list is a list of tuples, meaning, you know, items bundled together for one tuple and then just like a list of those. So what I'm going to try to do is describe every single edge one by one using one tuple each inside of the edge list. So the first thing I'm going to do, just, you know, to make this a little bit easier, is I'm going to ignore the indexes for the vertex list, and I'm going to say, let's describe everything happening from the 3 node outwards, or just to every other node. So the 3 node itself, I'm going to look at its connections from left to right. So the 3 node, let's just start by putting a 3 here. Maybe I should describe the legend real fast. The tuples would basically be the start node, and then the end node, and then the weight, if there was a weight, but we're doing an unweighted graph, so it's really just going to be a tuple of 2 items. The other thing to keep in mind is that because this is an undirected graph, it really doesn't make a difference what node is the start node and what node is the end node. You can just swap them and it's totally fine. For me personally, I'd rather, you know, sort before assigning the start node and end node. That way when I read the graph later, it's a little bit faster because I wouldn't have to check in both directions. But it really honestly doesn't matter right now. So start node and end node. So the start node here is 3 and the end node is going to be 13. So that's the first thing that we're doing. That's the first tuple. And then I'm going to say, what else does the 3 connect to? It connects to the, not the 6, it connects to the 12. Okay, so the 3 connects to the 12. Again, we could have said 12, 3, it wouldn't have mattered, but I'm just going to try to keep it sorted. So then what else does the 3 connect to? It connects to the 18, doesn't connect to the 15. And just confirm that if I'm looking at the 3, I can see 3 lines touching it. So that means, okay, there's got to be 3 tuples for the 3. So I'm going to say 3 connects to the 18. And now I've described everything having to do with the 3 node. I will simply continue. Let's see. Should I do like a new line? Maybe I should try to do a new line for every start node. So this is easier to look at. Okay, so I'm going to do that. And I'm going to say the next line is, we'll start at the 13 this time. So the 13 is also connected to the 3 because it goes in both directions with an undirected graph. But we already described that connection with that first row. So 3, 13 describes 13, 3. I don't want to duplicate edges. So forget about that. Let's look at what else 13 is connected to. It's connected to the 6. So I'm just going to put 13, 6, and then that's the end of the 13's connections. I could have used tabs for that. Hang on, let me do that. Okay. So now let's look at the 6 node. 6 is not connected to the 3. It is connected to the 13. But we already described the 13, 6 connection in the previous row, so forget that. And then I'm just going to look to the right. So the 6 is connected to the 12 and the 15, the 12 and the 15, and also the 18. So I'm going to do 6, 12. Maybe I'm going to do a copy paste here real fast just to make it easier. 612 and 615 and 618. So again, all I'm doing is describing, what other nodes the current node is touching, and I'm going to do that using a tuple that just has one node and has another node, and that's pretty much it. So when we're done with this, we're going to look at the 12 node. 12 node, it's connected to the 6, already handled. It's connected to the 3, already handled. And it's connected to the 18, not handled yet. So I'm going to say 12 goes out to 18. Okay, then we're going to look at the 15 node. 15 and 6, that's already handled in that third row. So forget that. 15 and 18, that is not handled yet. So we're going to do 15, 18. By the way, this is one benefit of going from left to right visually. All I really have to do is just look my eyes to the right and I'll see nodes that I need to take care of. And if I look my eyes to the left, I'll see nodes that I already took care of, if that makes sense. So now that we're done with the 15, let's see, we did 3, 13, 6, 12, 15. Let's just take care of the 18, if there's anything left to take care of. I can guarantee there's not going to be. Because every node, the 18 is the node on the farthest, the furthest to the right, so everything on the left is already handled. So we don't even have to put anything for the 18 node. Okay, give me a second to clean up this graph real fast. I think I want to maybe move this up a little bit. Okay. Now here's the thing though, we've only named node values. So if we wanted to, I don't know, let's say check to see if the, let's say we have an edge. We're looking at the 3, 13 edge. And we're asking now, do both of those nodes exist? The edge describes these two nodes. Do they exist? Or maybe let's look at the 3 here. And we want to figure out just, what other nodes does 3 touch? So we start iterating through all the edges here. How can we actually get a pointer to that node to manipulate it in the code? Right now it's okay because it's a diagram, but this is not very good storing values directly in this notation. In your code, you probably want to store pointers there, but maybe not necessarily smart pointers. They take a little bit of extra memory and it's kind of cumbersome, but we could store an index into this vertex list to make things a little bit faster. Let me show you what I mean. So first, I'm going to duplicate this list that we just made already. Duplicate it over here. And maybe I'll label the first one and I'll say, so we already have start node and end node. I'm going to say E underscore by value. So we're storing the edge list by node values. And then here, we're going to store nodes by their index in the vertex list. So what do I mean by index? Well, okay, right here, the first node that we're mentioning is the 3. Well, look at the 3 node in the vertex list. It's at index 0, right? So I'm just going to put a 0. That's it. Change it to an index. Then I look at the 13, that's index 1. And then I look at the 3 again, that's index 0. And then the 12 is index 3. And then the 3 again is index 0. And the 18 is index 5. If that was too fast, I'm sorry. Just rewind and play it back in slow motion. I think this video is already getting way too long. So then I do the same thing for every single other tuple. So the 13 node, that is index 1. So I'm going to put a 1 there. The 6 node is index 2. Go on to the next node. So the 6 node is index 2. And then the 12 is index 3. And the 6 is 2. And the 15 is actually 4. The 6 again is 2. The 18 is 5. Move on to the 12 node here. That's index 3. 18 node is index 5. And then the 15 is index 4. And then 18 again is index 5. So now on both sides, like in both of these edge lists, I'm representing the graph. It's just that one can be a little bit more efficient than the other. For example, if I was going to, let's just say I wanted to scan every single edge in the graph. Well, I could scan this list right here in linear time. So linear time based on the number of edges. And every single time I see an edge, I can jump directly to the corresponding vertex or node in constant time because I have an index. So for example, let's say, this 6 node touching the 15 node. So that particular edge right there. I want to be more interactive here. How can I do this? Okay. Suppose I want to do this node right here, this 612 node. And so that's going to be pointing to this edge right up here. I want to see, what's going on with both of those nodes. Well, if I was looking at the value-based edge list and I wanted to get a hold of, let's say, the 6th node itself, so I can like do something with that vertex, like delete it or move it or just whatever, I would have to then scan the entire vertex list. I'd have to go, this one, this one, this one, this one, this one, until I eventually found the corresponding value. This wouldn't really support duplicate values either. It would be kind of hard to do that. But I've slowed down the program. It's linear time based on the number of vertexes. And if you were already doing linear time based on the number of edges, this is technically still a scalable data structure, but it's not super fast. It could be faster. On the other hand, so like I just said, sorry for repeating myself, if we did the index-based edge list, it says 2, 3 here, which is the 6, 12. How can I find the 6th node? Well, I just look at index 2, and instead of scanning, oh gosh, hang on. Not as fast as I used to be. Okay. Dude, there's did you see that? A whole bunch of pink dots everywhere now. What have I done? Okay. So I'm looking at the 6, 12 edge. I see that the indexes are 2 and 3. That means in constant time, I can just jump directly to, I guess I'll put it in red. In constant time, index 2 right there, and index 3 right there. I do not have to scan the vertex list or the vector. I guess if it was a vertex list, like an actual linked list, then I'd still have to scan because it's linear time to do it. But if it's a vector or an array, I can just jump to an index in constant time, so it's way faster. So what I'm trying to say is that this representation is what you want to do in the code. When it comes to, I don't know, representing diagrams and stuff, I don't know. The one on the left is more human-friendly. So this is the basic idea for how to represent an unweighted and also undirected graph in the machine using the edge list method of representation. So I guess I'm going to cut the video. I hope you learned a little bit of stuff and had a little bit of fun. In the next video, I think I'm going to do weighted undirected graphs. And so I'm going to do 4 videos for this one representation type. I'm going to do unweighted, undirected, and then weighted and undirected, and then unweighted and directed. I'm going to do all 4 combinations. All right, see you in the next video. Thanks for watching. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. Sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? Just send me a comment. Whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness, which is coming for us all.